Hello again. For the second part, or the second major topic for today, we're going to be building our own Markov chain Monte Carlo process in order to estimate the posterior probabilities for a certain situation. So hopefully this will bring together some of the ideas we've been talking about. So bring together Markov chain Monte Carlo and some of the probability distributions that we've just discussed, and bring those together to show you how we can build our own Markov chain Monte Carlo process and estimate posterior probabilities. So it should be interesting and fun. So let's get started. Okay, so again, we've discussed Markov chain Monte Carlo, and we've discussed probability distributions. So let's use this information to build a homemade Markov chain Monte Carlo process to estimate posterior probabilities. Okay, so let's set up a hypothetical scenario. So let's say that you want to know what percentage of SMU students are happy that SMU courses are remote this term rather than in person. Of course, this is given our current situation, not in general. So let's suppose that you ask 25 students, 18 of which are happy that we are remote. So this is 72%. So then the question is, should we take this estimate at face value? How much do we trust this estimate? Or how certain or uncertain are we about this percentage being representative of the entire population? And so this is a question, we're going to collect data like this a lot of times during our research, right? We'll obtain an estimate, and we want to know how sure we are of those estimates. It's also worth spending some time thinking about how would you answer this using classical or frequentist-based statistics. Could we even answer this question with p-values? We could say that the data are not consistent with, let's say, a percentage of 50%, but how could we answer this question using a frequentist-based approach? I'm not going to discuss that. That's just something for you to think about on your own. But this sort of scenario is something that comes up often in all types of research, where we obtain an estimate and we want to know how certain and uncertain we are about that estimate. So what we can do is set up a Markov chain Monte Carlo process to estimate the posterior probability for our estimate of the percentage of students that are happy. Now, remember, for posterior probabilities, we want to test we're looking at the probability of a hypothesis given the data. In this case, instead of a specific hypothesis, our hypotheses are actually going to be every possible value for this percentage. So we're going to look at what's the probability that the true percentage is 0? What's the probability that the true percentage is 1? And every value in between. In theory, we'd look at every value in between. We're going to approximate this process. And this is what we're going to do pretty much all the time we're doing Bayesian analyses. We're not going to set priors to one particular value. It's rare that we have that kind of information, or that that's even what we want to do. Instead, our priors are really distributions of possible values that our hypothesis could take, and that's what we use for our estimation. So you'll see how that works. So in this case, our probability of our hypothesis given the data, so the probability that the true percentage of happy students is, we'll look at 10, 11, 0, 99%, and so on. In theory, everything in between, but because we're just approximating it, we won't look at every value. So for this scenario, we need two different probability distributions. One is we need a probability distribution for the prior probability of this percentage being any particular value, so our percentage of happy students. And then we need another probability distribution for the likelihood of the data given a particular percentage. So we need a likelihood, which is the probability of the data given a hypothesis. And we can use probability distributions in both of these cases. And when we'll use distributions that we just talked about. So first, let's think about our prior probability. So before collecting the data, what probability distribution best characterizes our beliefs about what percentage of students are happy that we are remote instead of in person again, given the situation. So you probably actually have a pretty good idea, right? You talk to other students and friends. So you probably have a good idea of how many students wish that we were in person versus remote, given the current situation. But let's pretend that you don't. We'll come back to that later. But let's start out and say, like, we have no idea. And therefore, we're going to use a uniform distribution. So we're going to say, before we collect the data, all probabilities of students being happy, or all percentage of happy students, are equally likely, equally probable. So we're going to use a uniform distribution for our prior beliefs on student happiness. So remember, a probability distribution in R for the density for a uniform distribution is used with this D unif. So the unif is a uniform distribution, and the D stands for density. And it calls for these arguments. The x is the vector over which to calculate the density, and then the minimum and the max. Then for the likelihood of the data, we need a different probability distribution. And this is a way to calculate the probability of the data given the hypothesis. So for our student survey, there's two options. So let's say we only gave them two options, whether or not they're happy that we're remote or they're not. And so we won't give them any intermediate options. So because of that situation, where there's only two options, then the binomial distribution is appropriate. So remember, the binomial distribution is a discrete distribution that we use when there are two possibilities. And so in R, again, we can calculate the density with the D binom function. And this requires the vector over which we're going to calculate this density, the size, and the probability of a success. So in this case, of a student being happy. But we can change. So for all these probability distributions in R, in the past, to plot them, we've used the densities. But what we can also do is randomly draw numbers from those distributions. And for those situations, we use an R here instead of a D. But otherwise, it's the same. So how can we construct this Markov chain Monte Carlo process? The first thing we're going to do is randomly propose a new value for H. So H is going to be the probability of students being happy. So randomly propose a new value for H from our prior distribution, which is a uniform distribution. So we can do that with this command here. So we're going to assign to a new variable called prior. We're going to randomly sample, so the R here, from a uniform distribution, one value, and our uniform distribution has a minimum of 0 and a maximum of 1. So again, we're saying, before we know any data, it's equally likely that our value falls anywhere within this range. So we're going to randomly sample one value from this range. And that's going to be our first proposal, our first proposed estimate for the probability, or I guess it's just our first proposed value of the percentage of happy students. Then what we do is we use this prior value in a binomial distribution to generate a hypothetical data set with our characteristics. So we're going to randomly draw from the binomial distribution one sample set of 25 individuals, right? So remember that that's how many students we surveyed. So we're going to sample from 25 individuals just once, and then the probability of a success, or the probability that the students are happy, we're going to use our prior value from here. Okay, so we're using the prior, our proposed probability as our prior, and we're going to use that in the likelihood. Okay, and so now, and we're going to assign that to a new variable called post. And so you can run both of these and just see what values you get. And then, if that value of H, so if our proposed value of the probability of a student's happy, if that results in the same number of happy students as our observed data set, then we keep that value. Otherwise, we try again, right? So this is our Markov chain. So if that proposed H results in the same number of happy students as our observed data set, we're going to hold on to that value. We're going to keep it. Otherwise, go back and propose a new value. And we're just going to keep going through this process over and over again. Here's another way to visualize this. So we have our prior as a uniform distribution between 0 and 1. We're going to randomly propose a new value of h, or our probability that students are happy, from the prior. That's going to be the input of our binomial distribution. So we're going to use that value to generate a data set from the binomial distribution. But this data set has the same characteristics as our observed data set, so it's the same sample size. And then, if the proposed percentage results in the same number of happy students as the observed, then we keep it. We're going to put it over here in this bin. Otherwise, we discard it, so we can put it in the trash. And if we repeat this over and over again, then we'll accumulate values for our estimate that are consistent with the data. Oh, I think I put, yeah, okay. So, yeah, so what we'll keep here, like after we do this many, many times, we'll have values of h that are consistent with the data. And the values of h that are more likely to generate the data will be present more often. So we'll get a distribution like this. And why that results, it's worth spending a little bit of time on that, right? So if we think about a coin toss, even though we know the probability of getting a heads or tails is 0.5, if for a certain sample set, we don't always get 50% heads and 50% tails, right? If we flip it twice, there's a good chance that we'll get all heads or all tails. And if we flip it 10 times, it's unlikely that we'll get exactly 5 heads and exactly 5 tails, even though the true probability is 0.5. So there's noise in these distributions, right? But the larger our sample sizes are, then the closer they're going to approach the true probability, the true frequency, right? So if we flip a coin 1,000,000 times, then our frequency of heads and tails is going to be very, very close to 50-50. But the smaller our sample size are, the more different they could be. And so what this means is that the correct value for our probability won't always generate the correct answer, right? So with the probability of 0.5, with the true probability of 0.5, you can still get, different counts, different frequencies, but depending on your sample size, that will determine how heavy these tails are around that expected value. And so it also means that kind of incorrect values will sometimes generate the correct answer, right? So a probability of 0.45 might generate 50% heads and tails for some data sets, right? But the further you get from the true probability, the less likely it is that you'll get the kind of observed or expected number of counts. And so that's what this distribution represents. And so that's what we'll be getting here, right? From these kept values, the values of our hypothesis, so the values of the proportion of happy students that are more likely to generate our observed value of happy students, are going to be present more often in our kept list of numbers. So hopefully that makes sense. We'll walk through this. So let's do this by hand. Okay, so round 1, so you guys can do this code as well. Of course, your numbers are going to be different because we're generating these from random numbers. So yours will be totally different. But here's some examples of when I did it. So here I ran this code, so randomly generating a prior value or a proposed value from our uniform distribution, and this time that was about 0.16. I used that to randomly generate a data set from the binomial distribution, so generating one data set of a sample size of 25, using our prior as the probability of success, and we get 6 successes here, so 6 happy students under this scenario. So we're going to discard this proposed value for the percentage of happy students because our observed value is 18 and this value generated 6 happy students. So we're going to discard that. Round 2, so we just do this again. Propose a new prior value from the same uniform distribution. This time it's 0.58. Use that as our probability of success in our binomial distribution of our sample size. This time we get 11 happy students. So again, we're going to discard this proposed value of the percentage of happy students, again, because it doesn't match our observed of 18. I do it again. This time, our proposed percentage is 0.83. That gives us 19 happy students. That's not our observed value, so we're going to discard that again. Next time, so round 4, we get our proposed value of 0.66. This does generate, when we use this in our binomial distribution, this does generate 18 happy students. So we're going to keep that. Okay, so hopefully that makes sense. Now, of course, this is going to take a really, really long time to get a good estimate here. So we're not going to do it this way, but hopefully that idea makes sense to you. If not, kind of stick with it until it does. So you should be thinking, as we're doing this over and over again, be like, you know what, this is the sort of thing that a loop would be good for. And you would be exactly right to think that. So I'm going to stop this now, and then we'll come back and we'll make this into a loop.